Dear students, welcome to the VLSI testing class. Today we are going to introduce a new topic, Sequential ATPG. Since we have known the combinational ATPG very well, we now enter a new topic, Sequential ATPG. In our last chapter, we already know ATPG for combinational circuits, but your manager now asks you to generate a test for sequential circuits. For the following circuit, can we generate a test to detect the SeqAT1 fault here? Please note that there is no scan allowed in the flip-flops. How can we do this? So in this chapter, we are going to learn sequential ATPG to generate test patterns for sequential circuits. And we assume that there is no scan or DFT available in the circuit. Here we have an interesting quotation. If life is a test, one should wish it to be short. This is true for test generation. In sequential ATPG, we wish the test should be as short as possible. Here is a table for our test generation. We already know how to generate tests for combinational circuits using dependent or friend algorithm. Now we will learn how to generate tests for sequential circuit. In this chapter, we will focus on single SeqAT fault model only. In this chapter, we will first do a short introduction, followed by two different approaches. One is time frame expansion, the other one is simulation-based method for sequential ATPG. And then we will discuss some issues for sequential ATPG, and we will conclude this chapter. This picture shows a Hoffman model for sequential circuit, which was proposed by Dr. Hoffman. In this model, Xi's are the primary inputs or PI, Zi's are the primary outputs or PO, and this rectangle represents memory elements such as flip-flop or latches. Small y's are the flip-flop next state. Big y's represent the flip-flop current state. Please note that this model can be used either for milli or more circuits. In sequential ATPG, we assume that there is no scan allowed, which means that we can only control the primary inputs. We are not allowed to control the flip-flop state. We can only observe the primary output. We are not allowed to observe any flip-flop state. Please note that faults are assumed to be in combinational circuits only. The memory elements, the flip-flops, the latches are assumed to be fault-free. There are many difficult challenges for sequential ATPG. First, flip-flop or latch states are not controllable. They are not observable. This is particularly difficult when the circuits are powered up with a known initial state. The second issue is very long runtime. For combinational circuits, we know that the worst case complexity for given fault can be 2 to the power of primary input. For sequential ATPG, the complexity is even higher. For a given 4, the worst case running time can be up to 2 to the power of primary input times 9 to the power of the number of flip-flops. In this analysis, we assume 9-value logic, which will be introduced later. This is a very large number. The third issue is that sequential ATPG consumes large memory space. If we want to use time frame expansion, we need to duplicate or replicate the circuit into multiple copies, which will occupy a lot of memory space. And eventually, even if we can generate sequential ATPG patterns, the fault coverage is typically very low. The fault coverage of sequential ATPG is typically much worse than combinational ATPG. In summary, sequential ATPG is a much more difficult problem than combinational ATPG. Now we have a short quiz for you. For a very small sequential circuit with 100 flip-flops, what is the worst case ATPG complexity? A. 9 to the power of 100. B. 2 to the power of 100. C. 100 squared. So what's your answer? Yes, it's 9 to the power of 100. This is a very large number. If you don't have idea about how large the number is, you can compare this number with the number of atoms in the universe, which is 10 to the power of 80. This number is even larger than the number of atoms in the universe. So this is a very, very difficult problem to solve, even for this small circuit. Now we will introduce the first time frame expansion method, the extended D algorithm, which was proposed by Kubo in 1968. The idea of time frame expansion is very simple. We simply replicate the circuit and connect these multiple copies of time frames by wires, as is shown in this figure. We replicate this circuit into 3 copies. The right time frame represents the future, the next cycle. The center time frame represents the current cycle. The left time frame represents the previous cycle. And we simply connect these circuits by wires. So there is no flip-flop. These 3 copies together becomes a very large combinational ATPG problem. So we can simply replace the clock cycles by memory space. Since we already know how to solve this combinational ATPG problem, we can simply apply our previous techniques such as the D algorithm or the Polden algorithm. The only difference is that the target fault appears in every time frame. So we can have multiple faults at the same time. The extended D algorithm is very simple. At the beginning, we select a target fault, and then we create a copy of the combinational logic. We set this to be time frame 0, and we generate a test for the fault in time frame 0 using traditional D algorithm. If the fault effect is propagated to the flip-flop, we continue fault effect propagation in the next time frame. That means we create a time frame on the right. Step 5. If there are values required in the flip-flop output, we can continue the justification in the previous time frame. That means we can replicate the circuit to the left. Now let's get back to our motivating problem. Consider this stuck at 1-4 in the sequential circuit. Let's use the extended D algorithm to generate a test. First, we create time frame 0 by removing these flip-flops. Small y1 and y2 are now inputs, and the big y1 and y2 are now outputs. If we want to propagate this 4 to the right, then we will need A0 equal to 1. If we want to activate this 4, y1, small y1 needs to be 0. This test is not done yet because y1 is not primary output, so we still need to propagate to the right. Now let's create a new time frame 1, and we will try to propagate the 4 effect to the primary output Z. To do this, we will need to control y1 equal to 1. In this way, we can successfully propagate the 4 effect to the primary output. But this test is not done yet because we have not yet justified this 0. So we need to expand the time frame to the left. Now we create a new time frame -1. To control this to 0, we will need to apply A-1 to be 0. In this way, we can generate a test which is 0, 1, 1. If we apply this sequence of input test patterns, we can detect the 4. Now, please do a practice by yourself. Consider this stuck at 0-4. Please use the time frame expansion method to generate a test. Please now pause the video and practice. Okay, back to the video. Have you generated a test successfully? Actually, this 4 is untestable by sequential ATPG. When we try to propagate the 4 to the right, it just keeps going and going without reaching to any primary output. So there is actually no way to propagate this fault. This is an example of untestable fault by sequential ATPG. What is worse, this fault can cause time frame expansion to the right endlessly, so it may cause memory explosion problem for ATPG. In summary, today we have introduced the sequential ATPG, which is a time and space consuming algorithm, and the fault coverage can be low. There are some faults untestable by sequential ATPG. In this video, we have shown our first time frame expansion method, the extended D algorithm, which replicates the circuit into many time frames. We propagate forward to the right and activate the 4 backward to the left. We can create new time frame to propagate or activate the 4. Before we end this video, we have some questions for you to think about. In combinational ATPG, we first perform for activation and then propagation. However, in sequential ATPG, we first propagate the fault to the right, and then we activate from the left. You'll note that the order of activation and the propagation are not the same. Do you know what is the reason? This is a very interesting question. Thank you for watching.